It's a great pleasure to be here and helping to celebrate the 190th anniversary of the precursor of this university. And oh, this come off. Somebody took this off. Right. So, as Derek said, I'm Carlos Frenk from the Institute for Computational Cosmology in Durham. And that is the famous Jeremiah Horrocks, in whose honor the institute where astronomy takes place here is named. And there you see him. He died rather young, but in that brief life he had, he was able to predict the transit of Venus and measure it as well. But I'm going to go a long, long way away from Venus today. I'm going to tell you not about planets, not about the solar system, but in fact, I'm going to tell you about the whole universe and how the universe, in fact, came from nothing. I will explain what I mean by nothing in a little while. So this is the building that, one of the buildings that Derek called, what did you call him, a spaceship or something? And so I'm going to tell you about how our universe was made. This is a very beautiful building that just came up. So we just opened it last year, built by a very famous architect in Durham, and called Daniel Libeskind, who his son was my PhD student. So that's why I managed to get an architect from New York to come and make this fantastic building. So as Derek said, I'm a cosmologist, and cosmology asks some of the most fundamental questions in the whole of science. Questions such as how did the universe begin? Small questions like that. What is it made of? How did it get to be the way it is today? And what is the long-range future of our universe? So these are all very old questions, the questions that go back to the beginnings of human civilization. I would probably say that human civilization began when an ancestor started asking these sort of questions. Now, so it's not just physicists and cosmologists who, of course, want to find answers, at least partial answers to some of these questions. They are of interest to people in many other disciplines. But what distinguishes us cosmologists from theologians or philosophers or artists who ask similar questions is that in our case, we tackle the problem from a rather narrow point of view, from the point of view of physics. And we then based all our studies of the universe on the laws of physics. I'll remind you what the laws of physics are. They are general rules about natural phenomena. They are derived empirically in the laboratory. And for example, you know many of those, I'm sure. Newton's law of gravity, Boyle's law of gases, quantum mechanics, relativity. These are all laws of physics. And they're all discovered on Earth experimentally, expressed mathematically, where these laws can be manipulated. But one of the deepest mysteries, if not the deepest mystery that I've come across in my life as a cosmologist, is that the very same laws of physics that apply here on our small planet Earth seem also to apply equally well everywhere else in the universe and at every other time, in conditions that bear no resemblance, the Big Bang, that bear no resemblance at all with the conditions here on Earth where these laws of physics are discovered. So that is a profound mystery. Why does the universe conform to the same laws of physics that apply here on Earth? I haven't got an answer to that. But we do, nevertheless, using this narrow approach to the subject based on physics, we have learned quite a lot about our universe. For example, we know to great precision that our universe is about 13.7 billion years old, and many things have happened since the Big Bang until today. And I'm going to be telling you a little bit about what our universe has been up to in these 13.7 billion years. Now, so let me just start from the beginning. The building blocks of our universe are galaxies. Galaxies are collections of stars ranging from a few million to a few 100 billion stars. It's a particularly bright galaxy, not dissimilar to the galaxy in which we live. We live in a galaxy called the Milky Way, and we are located 2/3 of the way from the center of the Milky Way. Now, this is one of hundreds of billions of galaxies in the universe. And just to give you a little flavor, I want to show you a movie made by a colleague of mine. Victor, could you put the lights out, please? In the University of Hawaii, of what's around us in the cosmos. So what you're about to see is a journey through our local universe. Everything in it is real. Okay, let's try again. Right, good. Well, no, I decided to leave him on, but at a good volume so you can hear what he's saying.
The constellations familiar from Earth, mapped here in 3D space by the Hipparcos satellite, quickly become unrecognizable as we drift toward the Orion star cloud 1,000 light years away. In the great Orion Nebula, massive luminous young stars light up the vast of gas and light years around. In the Horsehead Nebula, a dense knot of dust is silhouetted against red glowing hydrogen gas. Here comes another star cluster at the end of Rosette Nebula. Many clusters are scattered through our galaxy's disk, but only in such young clusters can we find stars still embedded in the gas that formed them. Not all nebulae are in the business of rearing stars. The Crab Nebula is a supernova remnant where a massive star exploded, leaving a spinning pulsar to blink at its core. Rising now above the disk plane and its obscuring clouds of dust, we see our galaxy in its full grandeur, 100,000 light years across. Earthbound astronomers cannot look at our galaxy this way. This model is derived from an image of another Milky Way-like galaxy, SEA-83. To the left are our satellite galaxies, the Magellanic Clouds, our nearest neighbors. The Andromeda Galaxy M31 and the Pinwheel M33 are the other large members of our local group, within 2 billion light years of all. This nebula in M33 is like the Orion Nebula, but far larger. If seen at the same distance, it would fill half our sky. M31 is the farthest object the human eye can easily see from Earth, but we will travel much further, following chains of galaxies out to the Virgo cluster. We pass Messier at 81 and 82. Messier 101, one of the giants of our neighborhood. And the beautiful Whirlpool Galaxy interacting with its satellite. Ahead now lies the core of the local supercluster of galaxies. We fly along the filament through the Ursa Major cluster, a region of 100 spiral galaxies. Our goal is near, the Virgo cluster with 1,000 member galaxies moving under each other's gravity, is the largest concentration we have for 100 million light years around. Our journey ends as we fall into Messier 87, the giant elliptical galaxy that dominates this cluster.
Okay, well, sorry about the sound. I think I called him wrong. It's Stuart Levy who is the voiceover. I hope you could hear what he was saying. Here it sounded a little bit confused, but if you didn't hear very well, the main message is that this is a universe around us. It's full of these amazing collections of stars called galaxies, and what I'm telling you about today is where the galaxies come from. And you'll find that the results of that are quite surprising. Now, I'm going to focus on two of the questions that I put up earlier. I'm going to tell you a little bit first about what the universe is made of, and then I'm going to tell you about how the universe get to be the way it is as shown in that brief movie. So this is one of the biggest surprises in physics and in science of the last 20 or 25 years is the answer to the question, what is the universe made of? So it turns out that the universe is made of some fairly bizarre components. And let me tell you what those are. So the ordinary matter, the matter of which we are made of, and the kind of matter of which stars, the sun, the earth, and us are made of, what we study in our chemistry books, and we can see in the periodic table of the elements, makes only 5% of what the universe contains. So normal matter is only 5%. And as I said, the normal matter is a material that we're familiar with. About 25% of the universe is also made of matter, but it's very different from the ordinary matter. For one thing, it doesn't shine, it doesn't emit light of any sort, and for that reason, we call this dark matter. I will tell you a lot more about dark matter, but suffice it to say now that it is completely different from the normal matter or ordinary matter of which we're made of. The lion's share of the universe is not even matter, it's a form of energy called dark energy. And what this component does is a mysterious form of energy that is causing, it opposes gravity, and it's causing our universe to expand at an ever-accelerating rate. I'm going to tell you a little bit more first before I come to dark matter about dark energy. It's not going to take me long to bring you up to the same standard as professional physicists, because the reality is that we don't really know much about this dark energy. We know it's there, so much so that some people got the Nobel Prize for figuring out that the dark energy is there, but we don't know much more than that. We do know quite a lot more about dark matter, and I'll tell you about that in a minute. So we've known that the universe has been expanding for many, many years, since the 1929, when this gentleman, Edwin Hubble, of Hubble Space Telescope fame, discovered that our universe is expanding. So this is in the halcyon days where astronomers were allowed to smoke in their offices, and they had blackboards, not these horrendous whiteboards that we have today. So Edwin Hubble discovered that all galaxies around us are moving away from us at a speed proportional to their distance. So what he discovered was that the universe is in fact expanding. So we've known that for a long time, but what was discovered at the end of the last millennium is that the expansion is getting faster and faster and faster. And that was a major discovery made by looking at very distant supernovae. These are stars that explode at the end of their life. If instead of Stuart I'd been narrating the movie, I would have told you that stars only live for a certain amount of time, because stars shine thanks to the fact that they have a nuclear reactor in the middle. Eventually they'll run out of nuclear fuel and they die out, as will happen to our sun. But stars bigger than our sun, 100 times bigger than our sun, end up their lives in a very spectacular event called a supernova. And these supernovae can be seen, as you see here, very, very far away. And by measuring properties of the supernovae, physicists and astronomers discovered that now nearly 20 years ago that our universe is expanding faster and faster and faster. So what that means is there must be something pushing galaxies that causes them to recede from us at an ever-accelerating rate. And that is what we refer to as dark energy. And although we don't understand what the dark energy is, it merited the 2011 Nobel Prize in Physics. Now, so what is the cosmic dark energy? So I said I don't have much to say about it, and this will bring you up, I said, to the standard of professionals. Some form of energy produces a repulsive force and is causing the expansion to accelerate. And the only thing we do know is that whatever it is, it has to do with empty space, what we call the vacuum in physics, and that's because most of the universe is empty. You maybe didn't appreciate that in the movie that I showed, but the distance between galaxies is enormous. You saw our nearest neighbor, the Andromeda galaxy that was mentioned in the movie. The Andromeda galaxy, the nearest bright galaxy, is about 2.1 million light years away. So light takes 2.1 million years to get from our nearest neighbor, Andromeda, our nearest bright neighbor, to us. And in between, there's very little. So the universe is essentially empty, and there's something about emptiness or vacuum that is causing the universe to expand at an ever-accelerating rate. And that's the whole story that I can tell you today about dark energy. We don't know a lot more than this. But we do know a lot more about dark matter, and so I want to tell you now more about it. And dark matter, as I said, is matter that doesn't emit light, and it plays a crucial role in the evolution of our universe. I will tell you later on today that if it wasn't for the dark matter, we wouldn't be here sitting looking at these beautiful pictures. So, how do we know the dark matter is there? Well, it's dark, we don't see it, but here's the first example I give you tonight of how the laws of physics are so hugely powerful. So we know dark matter must exist for the following reason. Astronomers are very good at measuring velocities, and they can measure the speed at which stars rotate around the center of a galaxy like this one. And when they measure the speed of the stars, the result is that the stars are moving much too fast to be kept in place by the gravity, or the gravitational force produced by the material that you can see. So you see here stars, you see gas clouds, and the amount of material in the stars and gas clouds is much too small to account to keep the stars in place, because they're kept in place just like the Earth is kept in place rotating around the sun by the gravitational force of the sun. The stars are kept in place by the gravity of the material inside their orbits, but the material we can see is not enough by a long way, by about a factor of 10 or so. So that is deduced using the laws of mechanics that are due to this man, Isaac Newton, that you see here, who's actually Horrocks, in fact, was earlier than Newton. Anyway, so this is Isaac Newton, and in fact, the other day I was in London walking around worrying about this question of dark matter. I was so lucky that I ran into Isaac Newton, who has come back to life again, now as a musician. And he is Newton. You can see the nose is the same, the hair, of course, is the same. And he's just reincarnated as a, I don't know if everybody, so soon I'm going to have to stop showing this picture because I find that many people don't know who he is anymore. But at any rate, the reason then that we know that dark matter exists is because there must be more material there that we cannot see producing the gravity that holds the stars in the galaxies together. So the image you should have of a galaxy is some pool of light sitting in the middle of a clump of dark matter that produces most of the gravity. And we call these clumps we call them dark halos. I never understood why they're called halos, because they're not halos, they're just clumps. I guess because cosmologists have this saintly demeanor. I don't know if that's the reason we talk about halos, but that's the technical word for these clumps of dark matter in the middle of which galaxies sit. And as I said, it's the dark matter that keeps them in place. Now, so this is one source of evidence for the existence of dark matter. There's another one, a little bit more subtle, but equally spectacular. And that is related to this picture you see here taken by the Hubble Space Telescope. Now, this is a picture of a galaxy cluster. I don't know if you could hear the narration of the movie, but Stuart talked there about the Virgo cluster. So clusters are collections of galaxies ranging from a few hundred to a few thousand galaxies. This is a cluster of galaxies, and you see many, many galaxies, most of which look like you expect a galaxy to look like this one or that one or that one. But in addition to galaxies, there are these other strange features, these arc-like structures that you see here. Well, what are those? Well, those are also galaxies. But these galaxies, these strange-looking arc-like galaxies, do not belong to the cluster. These are galaxies that are a long way behind the cluster, whose light has been deflected by the gravity produced by the dark matter in the cluster as it travels by in the vicinity of this gigantic clump of dark matter. So if you then deflect light, then the image is distorted. That's what lenses do. This is called the gravitational lens. And this phenomenon tells us there must be lots and lots of dark matter. So just to repeat what's happening here, I'm going to show you a movie in a second that illustrates this. But what's happening here is that these are galaxies that are very, very distant. That light, in fact, travels near this concentration of mass. When it does so, it gets deflected. And if light is deflected, the image of the object that produced the light is distorted, in this case, in this characteristic pattern. So this was discovered by Einstein about 100 years ago, not quite, almost 100 years ago. And here is how he described it in a letter to his friends, to his colleagues. That's the way people used to do science in those days, by writing to your colleagues. And I got this wrong. It's actually more than 100 years. So here he describes how the light is deflected when it passes by a body that is very massive and has a very strong gravitational force. And it is this deflection that distorts the images. So I have a little experiment here for you. Here is a picture from the Hubble Space Telescope. Admire this picture because this is the deepest picture that humans have ever taken. So this is a real image of the sky. Many of these galaxies, especially the small ones, are so distant that the light has taken most of the age of the universe to reach us. So these little galaxies are formed when the universe was very young. I'm going to tell you more about that. And you're seeing them here, not as they are today, but as they were about 13 billion years ago when they emitted their light. So we're going to use this as a background. And the experiment that we did at the Institute was to imagine that we put a lump of dark matter in the middle of this picture. And the lump is going to grow in mass. And as it does so, you will see what it does to the images of these very distant galaxies. So here is the clump that it's in the middle here. It's growing in mass artificially. It is done in a computer. But we follow the light rays from the background galaxies. And you can see that as this mass in this lump increases, then the images of these galaxies get distorted exactly in the same way. Maybe I'll play it again, since it goes very quickly, sorry. Let's play it again, Sam. At least some people know what I meant by that. My students had no idea when I said, play it again, Sam. Anyway, so here you see the same phenomenon. You see this massive object deflecting light from the background galaxies and distorting their images. And it is through this phenomenon called gravitational lensing that we can figure out how much dark matter the universe contains. And it turns out, roughly speaking, that the universe has about 6 or 7, on average, times more mass than the mass that we can see in the form of stars, galaxies, and gas clouds. So roughly 10 times more dark matter than there is visible matter. Now, so what is the dark matter? So this is a question that I've been trying to answer throughout my scientific career, unsuccessfully so far. And, but we have a very good guess as to what it is almost certainly. And it is almost certainly a particle, an elementary particle that was produced very soon after the Big Bang. So the distance here is very heavily distorted. This is only a fraction of a second after the Big Bang. And at that point, the universe had cooled enough that theories of particle physics predict particles should be created out of energy. And these particles are today's most favored candidates to be the dark matter. But the particles have not yet been discovered. I'll tell you more about that in a minute. So the technical word for this dark matter is cold dark matter, something that people here at UC Lan investigate in many ways, like my host, Victor, who makes models of galaxies needing dark matter, and in particular, this kind of elementary particle, dark matter. Now, so the working assumption of physicists throughout most physicists, not all, there are always dissidents, which is a very good thing in science. In this case, a tiny fraction of my colleagues would disagree with this statement. But the vast majority of physicists would agree that the key assumption in the subject is that the dark matter is some form of elementary particle that was formed in the early universe, and it is very different from the atoms with which we are familiar. I will tell you more about why we think this, but what surprised me a lot a few years ago was to realize that, sure, physicists do this for a living, but it's not just physicists who agree with this hypothesis. It turns out that politicians do as well. Now, this is Angela Merkel, and the Chancellor of Germany, and somebody asked Angela, what is the dark matter? And you can see here her saying it's a tiny little elementary particle. Now, it's not surprising. I don't know if people know, but she used to. She's now a little bit in decline, but she used to be the most powerful politician in Europe. She's actually a physicist, and she studied physics, the wrong kind of physics, if you like, solid state physics, but nevertheless, she's a physicist. Maybe it's not surprising. But it's actually, you can see here what our own prime minister answered when asked, what is the dark matter? She was pretty clueless. Now, of course, you can't do that with Merkel, who told her, oh, come on, get your act together. But at least Theresa May listened, and she eventually got it, that the dark matter is a small elementary particle. But not all politicians are as quick to learn things. Maybe sounds slightly paradoxical, but she is. For example, look at this fellow here. He was asked the same question. Then he had a master who taught him the truth, and did he listen to him? No. So that is not all politicians agree, but at least some of them do. I have a whole collection of pictures of physicists, but I won't embarrass them all. Not all agree with this, but I will leave that for now. And just tell you why I'm showing you these pictures. And that is this, because it illustrates the enormous difference between politicians and scientists. And politicians just tell you things, and then you just either take it or leave it. But often there is no evidence behind what they say. In science, it's all about evidence. This is the motto of the Royal Society, which is the Academy of Sciences in this country. And what it says here is nullis in verba, which means don't take anybody's word for anything. Go and prove it yourself. And that is the basis of science. We don't take anybody's word for anything. We try to demonstrate it there's various techniques to do that. And that is the essence of science and what distinguishes science from many other human activities, like politics, for example. So, the dark matter is almost certainly an elementary particle, and it would be very good to detect one in a laboratory. And that is, of course, part of the subject of experimental physics. Now, I don't know if any of you have ever met an experimental physicist. I'm a theoretical physicist. Victor is a theoretical physicist. Derek is an observational astronomer, close to a theoretical physicist. If you've never seen an experimental physicist, this is what they look like. And they go around doing experiments trying to discover, in this case, dark matter. Now, if the dark matter is what I'm telling you it is, a small particle, then created near the Big Bang, then these particles are everywhere. They are here in this room. In fact, there are plenty of them here. There are about 1 billion crossing your body. Every square centimeter of your body, there's about 1 billion of these dark matter particles per second going through your body. But you feel nothing because they just go straight through. That's why they're dark. They don't interact with anything. And that's why they're so hard to detect, because if you build a detector and try to catch one of these particles, you just go straight through the detector, leaving no signal. That's why physicists have been trying very hard for 30 years to discover these particles. It is possible with an ultra-sensitive detector to catch one of these, and there is a big race in the world to try to be the first to detect one of these dark matter particles from the halo of the Milky Way impacting on a detector. So the UK used to be, many of the ideas of dark matter detection, SCOLC, originated in the UK, where until recently there was one of the main experiments in the world in the Bowlby mine, which is, if you just drive east directly from here, you'll end up in Bowlby, which is very close to a place that maybe many of you have heard of, Whitby. Whitby is very famous because it has an abbey, but it's also very famous because that is the place where Dracula landed in the 19th century when he came from Transylvania. And it seems to me it's always very comforting that we're looking for dark matter next to where Dracula landed. But at any rate, there's a mine there called the Bowlby mine, a working mine, trying to build. So the reason why these experiments are conducted in mines is because the Earth is continually bombarded by what we call cosmic rays. These are particles of ordinary matter that impinge on Earth. They come from outer space and from the sun, for example, or from other places in the galaxy. And this is ordinary matter, but they hit the Earth, hit the detectors, and they produce interference with these very delicate experiments. That's what they take place in the Bowlby mine. And here is a bunch of people at the Bowlby mine. Now, some years ago, you can see what I looked like in those days. I don't look like that anymore, sadly, but please, I don't have to be down the mine. Now, here are all sorts of interesting people. There's one experimental physicist in that picture. And the reason you can tell who it is because for all these people, he is the only one who's not smiling. That's him, Neil Spooner from Sheffield University. And working in a mine is not something conducive to many smiles. This is Peter Ogden. I'm called the Ogden Professor of Fundamental Physics. He's not my dad. He is a person who, in fact, paid for the building that I show you and endowed my chair. This is James Sterling, who used to be the provost of Imperial College, and so on. So there are various people here, one experimental physicist. Now you can, of course, if we had discovered the dark matter, you would know, because that would make headline news that would be very difficult to miss. So the dark matter hasn't yet been discovered, but I'm about to tell you why, at least I personally think, it has to be this kind of thing. And so why is the dark matter so important? And the reason I gave you already a little preview is that without the dark matter, we wouldn't be here, because the dark matter is responsible for everything we see in the universe, and in particular for the fact that the universe is as exciting and interesting as that movie showed. It's not just some kind of boring, uniform distribution of matter, which it could have been, and it would have been had it not been for the presence of dark matter. So I'm going to now spend a little bit of time telling you about the reason for the title of this talk, which is, where do galaxies come from? And the answer is that gravity, the gravity of the dark matter, is the key player in this event. So where do galaxies come from? Again, this is a subject where physicists have made enormous inroads, a great deal of progress in the time I've been a scientist. When I started as a student many years ago now, we really had no clue of where galaxies come from. And I'm going to show you the progress that has happened in the intervening 30-odd years. So the story begins very soon after the Big Bang. In fact, it begins a very tiny fraction of a second. If you cannot see this from the back, there's a decimal point, 34 zeros and a 1. So that tiny fraction of a second after the Big Bang, that's where the story begins. And it's quite remarkable. And I'm going to show you empirical evidence, of course, in a minute. But it's quite remarkable that physicists can go back to that very early time and still be able to keep a straight face. And I will give you the evidence for that in a little while. Now, so my talk was called Everything from Nothing, How Our Universe Was Made. So it's about time I told you what we mean by nothing. I already gave you a hint when I was talking about dark energy. Nothing has to do with the vacuum. And that's, in fact, what we mean by nothing in physics. We mean the vacuum. Now, the thing about the vacuum in physics is that contrary to what the word means to most of us, the vacuum is not empty. Unfortunately, or fortunately, the vacuum is full of really exciting activity, full of energy. So here is the closest I could get to making a movie. Actually, I didn't make it. A colleague of mine in the Netherlands made this movie. And it's the closest we can get to illustrating what happens in the vacuum. So imagine you have a chamber in a laboratory, and you connect it to a very, very powerful pump, and you extract everything out of that chamber until the last molecule is gone, the last atom is gone, and then you go and examine it with a very high resolution instrument. You will see that. You think, well, wait a minute, I took everything out. How come there's all these bubbling going on? Now, what these particles are, and I'll warn you, this is the hardest part of this lecture. These are particles of matter and antimatter, which emerge out of nothing in the vacuum. So the vacuum is bubbling with particles of matter and antimatter, and as many of you will know, when matter and antimatter collide, they annihilate into energy, and this energy then decays again into matter and antimatter, which is continuously appearing and disappearing. This is the basis of quantum physics, and this is the basis of something called the Heisenberg uncertainty principle. It's the basis of nuclear power, the fact that the vacuum has this continuous synergy between energy and matter and antimatter. Now, so we know that. You can measure this in the laboratory. That chamber I was telling you about before, you can insert, when you think it's empty, you can put a little plate of metal, of gold usually, and you'll see that the plate moves, vibrates. It's called the Casimir effect, due to the fact that it's bombarded by the so-called virtual particles. They sort of exist, but they don't. It's all this very confusing world of quantum physics. Anyway, that was the hard part. If you didn't follow that, don't worry. I'm going to tell you what role these quantum fluctuations, as they're known, play. So very early, very soon after the Big Bang, this fraction of a second after the Big Bang, the universe was just essentially being born, and it was born in a slightly unstable state, which caused the universe to expand at a very, very rapid rate for a very brief period of time. This goes by the name of cosmic inflation. So the universe started life by inflating very rapidly. It soon stopped inflating, but the reason for this inflation was this vacuum energy that I just showed you. And as the universe expanded, these vacuum fluctuations couldn't disappear anymore and became imprinted into fluctuations of the density of the universe. So here are this vacuum fluctuating like crazy. The universe expands very quickly, and what happens is that these fluctuations become real perturbations in the energy density of the universe, meaning in the matter, in the ordinary matter, the little fluctuations appear, where one patch, for example, is slightly denser than another patch, and so the universe ceases to be uniform and is seeded with these small irregularities, which are known as quantum fluctuations. And the idea of modern cosmology is that this quantum phenomenon, these quantum fluctuations, provide the initial conditions from which galaxies, stars, planets, people emerge. Sounds pretty crazy. And the first time I heard this, I said, come on, you must be joking. This is not possible. I'm going to show you in a minute how this is, in fact, not only possible, but almost certainly what our universe did. So just to repeat, our universe is born in a slightly unstable state because it has this vacuum, too much of this good thing called the vacuum energy. The vacuum energy causes it to expand very rapidly, and these fluctuations, quantum fluctuations, become imprinted as small ripples in the content of the universe at very early times. And these small ripples are, according to modern ideas, the origin of everything we see in the universe. The next important event here is the production of dark matter. And then the next notable event in the life of our young universe, you can see why this is very compressed. This is only 350,000 years. It's 13 billion. It's just because this cartoon was made by a particle physicist, and all the particle physics happened here. All the astronomy happens there. So they distorted the distances and the times a lot. But nevertheless, now 350,000 years after the Big Bang, something very important happened. The universe was very hot at early times, and it was foggy. And the fog lifted 350,000 years after the Big Bang, which is the time when the first atoms formed. At that time, when the first atoms formed, the fog of the universe lifted, and the first light of our universe was emitted. Now, 350,000 years may sound like a lot, but if we scale this to the life of a human, it would be the equivalent of a few hours in the life of a human, whereas this would be the equivalent of a tiny fraction of a second in the life of a human, really, really, really tiny. This corresponds, on human terms, to a few hours. And at that point, the fog of the early Big Bang lifted, and the radiation of the Big Bang was free to escape, and allows us to investigate the conditions that prevailed in the universe at that early time. So the hypothesis then, and I'm going to now tell you where, give you the empirical evidence, but the hypothesis is that these tiny quantum irregularities were amplified by the gravity of the dark matter, leading to the emergence of galaxies. So I've now told you that about 3 or 4 times, and because it's an odd concept, but it is a concept very solidly grounded in modern science. But I often wonder, when I'm giving talks like this, what would this gentleman or that one do if they walked through the door? They, of course, knew about galaxies, and they heard these physicists saying that these galaxies come out of quantum fluctuations of the vacuum. I know what Einstein would do. He would, I'm sure, make a face. What Newton would do, well, he would reincarnate as a musician and say, I want nothing to do with physics, until he heard the rest of this talk. Because, as I said, what I'm telling you about is based on the laws of physics. And a key point about physics is that whatever you say must be testable. So one of the great things about my profession is that I can wake up in the morning and come up with a completely crazy idea. My wife says I do that every day, but I still get paid at the end of the month, so long as my crazy idea is testable. So I'm not allowed to come up with crazy ideas that you cannot test. But if the idea is testable, it doesn't matter how crazy it is, then it is real science. And there are few things crazier than to tell you that we all come out of a quantum fluctuation produced when the universe was a tiny fraction of a second old. That is very, very strange. But here is the evidence. So as I said, the early universe was very hot. And as it expands, it cools down. And this heat from the early Big Bang was emitted about the human equivalent of a few hours. And it brings us news about the conditions that prevail in a universe at that time. So as the universe expands, this radiation has been cooling down, and this radiation is here at a very low temperature. It was very hot early on, but it's been expanding, traveling for nearly 30.7 billion years. It's cooled down to a mere 2.7 degrees above absolute zero. But this radiation was actually discovered experimentally with a very simple instrument, a radio horn, in 1967 by these two gentlemen, Arno Penzias here and Bob Wilson. It was a completely accidental discovery. They had built an antenna, a radio antenna. They were interested in detecting radio waves from the sun. That's why they built a telescope, a radio telescope. And to their annoyance, they found that even when they didn't point at the sun, they were getting a signal. Wherever they pointed in the sky, there was this signal which looked the same from every point on the sky. So they were very frustrated because they didn't know what this was, and it was interfering with their attempt to measure radio waves from the sun. So it's one of the most beautiful stories in physics, because these people worked in Bell Labs in New Jersey in the US, and next door to New Jersey is Princeton University, where 3 of the greatest physicists of the 20th century, one of whom is still alive, Jim Peebles, who was a student then, and his supervisor and colleague. I'm going to talk about his colleague in a minute. They had figured it out. They had figured out that the universe had been very hot a long time ago, that it had been cooling down, and that this radiation should be permeating the whole of space. And because it comes from the Big Bang, it should be the same everywhere. Science and Wilson didn't know that. Accidentally, Bob Dickey, who was the supervisor of these other two students, it's an amazing story. He got on an airplane to go to Washington, and the person sitting next to him happened to be the boss of Bell Labs. So they got chatting, and Bob Dickey immediately realized what these people had. Apparently, he landed in Washington, took the first plane back, missed his meeting, and went straight to the lab, called Jim Peebles and David Wilkinson, who was the other one, sat them on the desk and said, "Boys, we've been scooped." And sure they had. So it's these two characters who were credited with having discovered the Big Bang, but it was these other three, whose I didn't even have a picture of them, who actually understood what was going on. Now, so let me just then tell you how, briefly now, the rest of the story. So, and the evidence, which I haven't really shown you yet. I'm about to. As the universe expands, these small quantum fluctuations, which are no longer quantum fluctuations, are real ripples in the fabric of the universe. They grow, they amplified by the force of gravity, and by the time this radiation, which by the way we call the microwave background radiation, is emitted, then these fluctuations have grown a little bit bigger. They're still very small, but bigger than they were, and there are points in space where, as I said before, matter is slightly denser here than there, or slightly hotter in one place compared to another. So these radiation should not be uniform. It should have hot and cold spots. And these hot and cold spots were predicted, in fact, by Jim Peebles, as it happens. He predicted in the 1980s that if you measure the temperature of this heat from the Big Bang, it shouldn't be uniform. It should have a pattern of hot and cold spots. So he made that prediction in the 1980s. And in 1992, in fact, the 22nd of April of 1992, this picture was published by a NASA satellite called COBE, for Cosmic Background Explorer. And what you see here is a map of the temperature of the heat left over from the Big Bang. And what you can see is that this temperature is not uniform. There are some hot spots and some cold spots. The resolution is not great. This was the first image ever taken of the temperature of the Big Bang, if you like. And it was one of the great discoveries in science. Actually, I got the date wrong, April 24, 1992. There was this glorious front cover in the Independent newspaper. I'm still waiting for modern newspapers. Well, they almost don't exist anymore, but whatever we have now to come up with a front cover announcing a big discovery. Now, so I'm going to leave modesty to one side. I played a role in this, and it's actually featured here in the front cover of the Independent. You probably can't see it from the back, but maybe the people in the front row can see. It says here, Carlos Frenk, an astronomer at Durham University, said yesterday, "Oh, wow." So that was my contribution to the discovery of the Big Bang. My great contribution to the sum total of human knowledge was, "Oh, wow." And this was wow, because well, for many reasons. One of them is that I've been teaching at a school in Sicily with the main person behind the discovery, and a few weeks before, and he wouldn't tell me what they had. Anyway, the thing is that it was a wow moment, and it was just incredible, because the theories had predicted that this pattern should exist, and it was finally discovered. So my epitaph, my wife knows, will say, "Oh, wow." Now that pattern was measured 10 years old. That one, George Moore, the person I was teaching with in Sicily at a summer school, and I tried everything. So I knew the experiment was there. I knew they were taking data. I was desperate to know what they had. And I tried everything you could imagine. I took him to the best restaurant in Erice. I bought him the best wine, and I couldn't get a peep out of him. At any rate, he got the Nobel Prize for that. And that radiation was measured 10 years later by the satellite called WMAP, where the W is one of the three people I told you about, David Wilkinson, who designed the satellite, the Bob Dickey student, together with Jim Peebles. And sadly, he died just before he saw this picture, and the W is his name, Wilkinson. Then the next experiment took place another 10 years later, now by the Europeans, by the Planck satellite, and this is the latest image of this kind that we have. And I want to show you this picture. Now, this is a technical picture, plot. The details don't matter at all. You don't care what the details are, but I want to tell you what it is. So here's Jim Peebles, by the way. So what this is a mathematical prediction for the nature of these hot and cold spots. So the technicalities don't matter. For those of you who are technically minded, this just tells you the difference in temperature between 2 points on the sky as a function of how separated they are. Point is, this is a prediction made based on the laws of physics, manipulated mathematically in 1982 by Jim Peebles. And as you can see, it's not trivial. There's all these bumps and various features that we understand from physics. Now, so that was the theory, and these are the measurements. The measurements are the points here with what physicists call error bars. So these are the experimental measurements taken by the Planck satellite. And this is just one of the most amazing things that I've seen in my whole life. And I hope you'll agree that it's also one of the most amazing things you've ever seen. So what you see here are two things. Firstly, theoretical predictions about how our universe was born, shown here in green, formulated using the language of mathematics based on the laws of physics that we know and love from Earth. So it seems to be quite remarkable that for some reason, in this little corner of the universe, 2/3 of the way from the center of a perfectly ordinary galaxy, there's a planet called Earth, which is, like we now know, many, many millions, possibly billions of other planets, and yet a species of life form has evolved with the ability to make predictions about how the whole universe began. That is the green line. And also, the same species of this form, this life form, has the ability to construct machines which they launch outside their planet that can make these measurements that are really, really delicate, because it's the difference in temperature is not big, is 1 part in 100,000. So those spots that you saw in the picture differ in temperature by 1 part in 100,000. And the two agree amazingly well. So to me, this is not just one of the great achievements of cosmologists and physicists, but I regard this as one of the great achievements of humanity, on a par with, Beethoven's symphony or a Rembrandt picture, or whatever it is you think humans are capable of doing when they are at their best. So now that is the empirical evidence that I've been advertising for quite a while. And it tells us that all these very bizarre story I've been telling you about before is very likely what happened, because all that story is encapsulated in the green line. So the green line has quantum fluctuations from has inflation, has quantum fluctuations, and has cold dark matter. So those are the ingredients that go into these predictions, and then along with the laws of physics. So I'm nearly at the end. I just need to tell you what happened in the intervening, this is the map, 350,000 years after the Big Bang, 13.7 billion years. So I just need to tell you what happened in the intervening 13.4 billion years, but it won't take me long, because that's the easy part of the story, because we now have all the ingredients. We know how things started, and we know physics. In this case, the equations cannot be solved with a pen and paper, but we can solve them with a big computer, and the computers are amazing at doing physics. So I'm going to tell you now how you make a virtual universe, which is what I'm going to finish off with, because we now have the ability, since we understand physics, to recreate the universe in a computer. We know the starting condition, those patterns of hot and cold spots that I show you. We know physics, so we program a computer to solve the equations of physics and produce in our laboratories a virtual universe. So how do you make a virtual universe? Don't try this at home unless you have a big computer. So all you need is to know where to start. You need to make some assumption about the contents of the universe, that the dark matter is called dark matter, for example, and that's all. Then you need to solve the equations of physics. These are quite a lot of those, relativity, the Newton's mechanics, all sorts of very exciting, interesting physical laws. You program a computer to solve those equations, which, as I remind my students continuously, the computers are a lot better than they are at solving equations, partly because they work all the time. They don't take time off, and they never answer back, and they always get the right answer. Trouble with the computers, they only do what you tell them to do, whereas the best students do exactly the opposite of what you tell them to do. At any rate, you go then away and wait for a while, maybe a few months, and see what happens, what comes out. So I'm going to show you what comes out of these computer simulations, as they're called. So this is the halo of the Milky Way. You're going to see it forming, and here are these quantum fluctuations from inflation, these little inhomogeneities that you see there. And what you're going to see is how these inhomogeneities are amplified by the force of gravity as the universe expands. So it's just this small inhomogeneity. It's a little bit of universe that's slightly denser. Then it has a little bit more gravitational attraction. So eventually, in the fullness of time, matter accumulates around this small perturbation, and these lumps begin to appear, which grow bigger and bigger and bigger due to the fact that the gravity, more and more mass is accumulating, so it attracts even more mass. It's called an instability. And my movie stopped here a mere 190 million years after the Big Bang. I don't know why. Let me see if I can persuade it to start again. So here it starts again. Here's the clock in billions of years. So that's 70 million years after the Big Bang. 80. So you see these fluctuations then growing. And see if it goes past that point. I don't know why it stopped. It should continue to the present day, but we'll see in a minute. So these amazing patterns form. This is something called, well, on larger scales, it's called the cosmic web. This is a version of a cosmic web. This is almost like a web of filaments. It's a huge amount of structure that emerges from those quantum fluctuations. And you can see how bigger and bigger lumps are forming just because of the force of gravity. You're looking only at dark matter here. I'm going to show you visible matter in a minute. This is just dark matter. And you see a big lump forming here in the center. This is the clump of dark matter where the galaxy will eventually form. And well, it's only 1.5 billion years, but it now gets a little bit boring. The object just keeps getting bigger and bigger and bigger. I mean, it's a beautiful picture. In fact, we won an art prize actually in Germany. Actually, not with this one. So this is what we won the art prize for. So this movie shows you what you would see if you were fortunate enough to be able to see the dark matter. And at the present day, if you were able to see dark matter and travel at many, many, many billions of times the speed of light, because we're going to go very fast through the universe here, this is what you would see the universe has produced, simply from these quantum fluctuations of inflation amplified by the gravity of the dark matter. So that's what the universe would look like if you were able to travel very fast and see the dark matter. You see all this huge number of little clumps. Most of them contain a galaxy in them. So the billions, hundreds of billions of galaxies that I talked about at the beginning, where here you see a small fraction of them, but it gives you an impression of what the universe of dark matter looks like. There are these filaments, these big streaks here called filaments, and the intersection of which particularly big lumps of dark matter form. So this is the very easy calculation. We've been doing this for, well, I started my career, not quite, but very soon after I started, I've been doing these simulations, and they're very, very simple. You just need a computer, and you need essentially to solve just a few equations. But it's only the dark part of the universe, which of course we cannot observe. Now, in the last 5 years or so, there's been a breakthrough in this subject where physicists have learned not only how to solve the equations corresponding to the evolution of dark matter, but also the much more complicated equations corresponding to the evolution of the ordinary matter, the matter that eventually turns into stars, galaxies, stars, planets, and people. We haven't made people yet in a computer, but just give us enough time. And so I'm going to show you now a movie which is very recent, and this is this breakthrough that I've been telling you about before. It's something called the Millennium. Sorry, it's called the Eagle. The previous one was the Millennium. It's called the Eagle simulation. And what you're going to see here now is a simulation not only of the dark matter, but also of the gas in the universe and the stars that make up galaxies. So we begin here again very early on. These are the quantum fluctuations again that are being amplified. This is still dark matter, but we're going to cut to gas in the universe in a second. So this is called dark matter. Now you can see what the gas is doing. So the dark matter is most of the gravity, and the gas is only a small fraction, but it follows the clumps of dark matter. So you don't see the dark matter here, but behind all these gaseous clouds, there is clumps of dark matter. And here's how a galaxy like the Milky Way formed. So here's the gas before it turns into stars. And now we're going to cut to the stars that have formed in the simulation. And this is still very early days, only a few billion years after the Big Bang. We go back to hydrogen gas, which is what most of the gas in the universe is. And you can see the growth of this object, which maybe reminds you of galaxies that appear in posters and things like that, with spiral arms and all the features that real galaxies have. We're going to cut to stars again in a minute. And then that's what came out of a computer. And this is not a computer animation. This is a solution of the equations of physics. We'll zoom out so you can see that there are many like that one. In fact, hundreds of billions in a real universe. In our computers, we can only simulate a few thousand. Now, so here's a very deep image that I showed you before. And here are some images of galaxies. And these galaxies don't come from an observatory. They don't come from an atlas of galaxies. They came out of a computer. So these are virtual galaxies made in one of our big supercomputers at Durham, which in fact is one of the biggest supercomputers in the country. And all it does is compute virtual universes. So I'm coming to the end. So I have been telling you quite an unusual and surprising story about how our universe began. It started off with this very strange, exotic phenomenon of quantum fluctuations when it was a tiny fraction of a second old. And by following the evolution of these quantum fluctuations, by using the known laws of physics, we can end up today making virtual universes in a computer. So here's what I told you. The story begins very soon after the Big Bang with these quantum fluctuations. We see them reflected in the pattern of hot and cold spots, in the temperature of the heat left over from the Big Bang, emitted when the universe is 350,000 years old. And it is these small ripples that eventually produce, when you run them through a computer, the universe that we see today. So I've nearly come to the end. What is there left to do? So I can see some young people here. Well, have we done it all? Certainly not. So the subject is full of open questions, and there are three big ones, which I have illustrated here with one of my favorite pictures. This the Garden of Early Delights by a German painter called Hieronymus Bosch. And there are three parts. There's Earth here, is the main part of the triptych. This is paradise, and that's hell. Now, so I think here on Earth is the question of what is the dark matter, because you can see how successful these simulations are, telling me that the dark matter has to be an elementary particle. Otherwise, the universe wouldn't look the way it does. And of course, here I'm only showing you the successful simulations, but I have an office full of failed ones where we had the wrong kind of dark matter and the universe doesn't look anything like the real one. So that, I think, is an earthly question. It's a question that experimental physicists, I think, are on the verge of discovering. So that is, I think, the next big breakthrough will be when you wake up in the morning and put the radio on and hear that the dark matter has been discovered. So that's for the Earth. For hell, I put the question of what is the dark energy, because that really is a hellish question, and I don't really expect that my contemporaries will answer that question. I'm not even sure that my students will answer that question. It really is very tough. It goes to the very essence of space-time. I think it goes to beyond the physics that we know today. So I put that one here in hell and in paradise. Well, in paradise, I left the biggest question of them all, which is, how did the universe actually begin? We know it began with a Big Bang, but with no idea of what went bang or why it went bang. And I'll stop on that.